Thank you. Thank you very much. Hello and good afternoon, everyone. I'm Dr. Madhumita Sahu. That's a great intro. Thank you. Thank you for inviting me to this 5-day workshop on application of remote sensing and GIS in research. And let me share my screen with you. Will it be okay right now? Okay, okay. Uh, Can I share my screen? Okay, okay. Yeah, just a sec. Now it's okay. Now you can see, right? Okay, just a sec. Okay. So, hello everyone. Thank you for this great introduction. And yeah, a short intro on my research experiences. My research mostly focuses on groundwater resource management, and I have used remote sensing and GIS. First, as you introduced, that groundwater is a very precious resource, and even though our entire Earth's surface consists of 70% of water, still groundwater or freshwater resources are very not so much available to everyone, and groundwater is one such resource which is not available or not economically available to everywhere. So the water occupying in the subsurface saturated zone is considered as groundwater, and since it is present beneath the earth's surface is very important at this point of time. While introducing how we manage the groundwater resources by applying remote sensing and GIS, it is really paramount to take into account that it's a hidden resource. Another thing is it is regarded as renewable natural resource, and that's why we rely on it. And in the case of, or in the scenario under which that we are saying the climate change will be affecting our water resources a lot, and under that condition we rely groundwater resources more and more. Our reliance has increased on groundwater resources. So we know that it's a hidden resource and it's a renewable resource. So next is, let me introduce you how we do it. So we are all aware of the surface water system balance equation. Um, Hello, can you just be a little interactive? Because I think I may lose the connection. So it will be great if you are interacting with me. Hello, hello. Yeah, if you guys can interact with me, saying yes or no or something, so that I can understand that you are there and I haven't lost the connection. Hello? Um, can you hear me?
Yes, ma'am, we can hear you.
Okay, okay. Just say yes or no so that I can be sure that you are still there. I'm not talking to myself. Yeah, okay. So we are at understanding the groundwater system water balance. Before that, we are all aware of how the surface water system balance works, what goes into the system, what comes out of the system, and how the surface storage is calculated. So, in the hydrologic cycle or the water cycle, if we are taking the surface water as our system, surface water system, so what goes into it as a positive term are the precipitation, the water that sips into like the surface water bodies, and in case of evapotranspiration, the E and T are evaporation and transpiration, the interception losses, they are considered as the negative terms. When we change our perspective to groundwater system, in the groundwater system, we take the infiltration, the water that sips into the groundwater, the seepage, everything as the positive terms, whereas anything that we extract from the groundwater, we take it as a negative term. The evapotranspiration, the groundwater we extract from the wells, if it is lost to the surface water bodies, there we take it as negative terms. So keeping it in mind, we construct or we get into the fundamentals of the remote sensing and GIS and how we apply it for the groundwater system. So the question arises that mostly, if the groundwater system is a hidden resource, so how can from space or from far away places a satellite or anything any devices they can sense it or see it or like sense the changes that are happening in the groundwater system. We know the principles of remote sensing relies on the reflection of light from an object, detection and measurement of electromagnetic radiation that is emitted or reflected from distant object. Now this type of remote sensing is termed as the multispectral remote sensing, and it's used in multiple areas ranging from disaster management, agriculture to mineral exploration. And this is the most common application of remote sensing and GIS you will come across on a daily basis. And maybe most of the resource persons in this workshop will most likely deliver lectures on this particular type of remote sensing. For groundwater practices or the groundwater hydrologist, which we are, we rely mostly on this multispectral remote sensing partially, but mostly our focus goes to geodetic or gravimetric remote sensing. When I say geodetic remote sensing, it measures the dimensions and form of the earth, the location of objects on its surface, and the changes in the figure of the earth's gravity field by means of satellite system. And the gravimetric remote sensing that measures the strength of the gravitational field of the earth that is influenced by the changes in the mass distribution of the earth. So we always say that the earth is round, but that's a vague idea. It keeps on changing. The form or the form of the earth keeps on changing. It's basically round, but it keeps on changing based on the mass distribution that happens or that is owed to the movement of water on our Earth's surface. And this surface water can be ranging from the groundwater to all the way to the atmospheric water that keeps on moving in our atmosphere, in our Earth's um, in our beneath the earth as in the groundwater case, and above the earth in our surface water case. So as the water moves throughout the earth's system, various system, atmosphere, surface, beneath the surface, the change happens based on the mass distribution. So this mass distribution primarily influences the movement and distribution of is influenced by the movement and distribution of earth's water, all the earth's water, and that kind of impacts the gravitational field. And this gravitational field, when it keeps on changing, that kind of can be detected from satellite or remote sensing objects. This is the case of purely gravimetric remote sensing. It's not very common to use, mostly by water resources people, but if you are interested in groundwater resources or mineral exploration, which not exactly the mineral, but if something is related to water distribution or how this can be affect something which can affect the magnetic field of earth, that can be sensed with this gravimetric thing. So when we talk about the movement of water in the earth system, we visualize this particular slide, and based on our groundwater system balance and the balance, the entire concept of gravimetry sensing is based on. So the various data which we use, like the slope and drainage density, everything we take from the topography, then the geologic landforms likely to contain the relatively permeable strata. Mostly the groundwater system relies on how the geology is there beneath an area or a catchment. And apart from that, what kind of geologic material is there? If it is highly permeable, low permeable, alluvial content, sand, silt, what kind of geological landform we are going to encounter? Based on that, we can get an insight that how much infiltration can be happening, how easily water can get recharged into the groundwater system, and how easy it is to extract water from that kind of geologic landform. Then the information on water bodies, localized gain or loss of stream flow, if there are perennial rivers or springs, and some information, in fact most of our information lies, or we kind of try to correlate most of our information with the groundwater wells which are present within that catchment area. If we are going to do a groundwater system management for a catchment area, we try to look into this data, and the reservoirs and canals and the seepage losses which can occur from the reservoirs and canals, how it can impact the groundwater sources. So these are the various information we look into. Primarily these informations. There could be additional information if they are required. So apart from that, this information, we always go for precipitation, because precipitation is the source where we get most of our water. From the atmosphere it reaches the ground, and from ground to groundwater. The river system, the river, stream, lake, reservoir water levels, the soil moisture data, evapotranspiration, and the groundwater level data are actually the basic data which are used by researchers to start their groundwater resource management problem. So usually about the precipitation, rivers, soil moisture data, evapotranspiration data, groundwater level data, you can get a few of these data from the field. And some of this data have to be derived from other kind of sources. So we will look into what are the different sources which we can get our data from. Get it from the IMD. IMD provides, yeah, I have given the links for the different data sources. If one catchment has got a network of rain gauge systems, then it's great. We have got primary data sources. If not, then we will go for the IMD dataset. IMD gives data at a gridded scale. And now the gridded scale has been refined to like which is like 10 kilometer by 10 kilometer or something. So you may correct or you may check it if you're interested in that data. If you're going for a bigger scale or like global scale, you can go for the Global Precipitation Climatology Center data. They also include data from IMD and other sources, like other national and international sources, and their data has got some data from, let's say, the satellite precipitation data. They also include. So they are a combination of all the data sources on precipitation, and they kind of integrate everything and give a gridded set of data. So if someone is interested in resource management like surface water or groundwater and they're looking for precipitation data, these are the most go-to data sets which we usually prefer. The soil moisture data, mostly soil moisture is another important yet very difficult to measure in catchments at a catchment scale. If you're going for a modeling thing, soil moisture data is very important, but it's hardly, people don't usually keep a regular soil moisture information for a catchment scale. If still we are looking for like first hand or primary data set, some people may be able to get a graded data set or something, but the go-to data sets we usually go for Copernicus Climate Data Store, SA data, the global soil moisture data. For evapotranspiration, our go-to data set is usually MODIS, and yes, mostly it gives data at 8-day interval or 15-day interval, and MODIS dataset is widely used. And last but not the least, the groundwater level data. Usually we go for the primary data sources, mostly the groundwater level data or level information which we collect from the wells, or the GRACE data set, which stands for Gravity Recovery and Climate Experiment. This is a satellite based program which gives gravimetric data, and most of my work was related during my PhD was related on the GRACE data and how to use the GRACE data for groundwater level information retrieval. So before that, we can go to how things which we collect, like the information we collect at first hand information which we collect from the field, how they can be used. The first one is like if we have got setup or network of rainfall, rain gauges or wells or anything, we have got instruments to collect the rainfall data, or if you have got a data logger fitted to a groundwater well, which we get the groundwater level information. So they are available at a point scale. If you can see the figure 2, they are available at point scale, let's say. But these point scale data are fairly not possible for us when we go for the softwares in which we do the modeling. Unless we are doing a modeling which is just for the point source, mostly at this day and age we go for the softwares like ARCSWAT or other hydrological models like mod flow, or other lumped base model or distributed model, which every time we go for a spatial data case rather than a point data case. Some of the softwares, they are capable of changing this data, point data, to spatial data, but mostly these data sets are preferred in a spatial form or an aerial form. So one of the methods to change the point data to spatial data, transform it, is thief and polygon method, where we average out our polygon for a given point data. The other methods could be kriging or natural neighbor or inverse distance weighting. There could be a lot more examples of uh, how we transform point data to spatial data. For this purpose, like we transform point data to spatial data, they can be done with the help of GIS. GIS, the Geographic Information System, it has a lot of wide applicability, but the starting point is to transform point data to spatial data for various purposes, for modeling purposes, for mapping purposes, and we usually go for ARSGIS, QGIS, GrassGIS, or there could be some more other players in this field of GIS. The ArcGIS is widely used, and it's not free, but yes, sir. Okay. Is it visible? Okay. Okay. So as we're discussing, the ArcGIS is not a free software, but the QGIS, GrassGIS, and R are free to use. So if someone is interested in using them, they are free to use. They are easy to learn. The all of them, in fact, are easy to learn. You will find a lot of resources online, where you can download them, install, and start using them. So when we go for the use of GIS in groundwater resource management, the first thing we go for is like the groundwater level prediction, which is widely uh, used, like widely. This is the one thing which we go for in GIS. We try to predict, or we try to model the groundwater level variation using GIS. Which sometimes the most important thing in GIS is to map how the groundwater level variation happens around the catchment, and that's why we go for the GIS methods. So when we try to get the groundwater level data, we usually go for the data or the groundwater level variation information from piezometers and wells that are present within a catchment. Certainly, we do have a lot of groundwater around our country, but the information is not regularly recorded. So we always end up with limited to no data. And of course, there are certain places where there is no groundwater well, and there we can't just have missing patches in our map to say that there is no groundwater or the information is not available. So GIS kind of helps in filling up those gaps and tries to give a regular or continuous map to us, or continuous surface map, as you can see it here. As it gives us the information how the groundwater level can vary within a catchment. So the GIS groundwater maps are important, and in fact they are the basis of our groundwater modeling. So the groundwater source in our country is Central Groundwater Agency, the State Groundwater Agency, and the Central Groundwater. Yes, yes. Okay, 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 okay. Yeah, sure. Uh, can you see it now? Okay. Is it visible? Okay. Everything okay? I'm at slide 11. Okay, thank you. So the primary data source for groundwater is Central Groundwater Agency and the State Groundwater Agency. They collect the data, and they are kind of deposited in a repository called India Varis. India Varis has got a very good repository on the groundwater label around the country, and the problem and the solution both lie at the same time. The data frequency is most likely the biggest problem which we usually face in our groundwater modeling. The data frequency at which the groundwater label data is recorded in our country is like seasonally. So we get one data in 3 months. So it's like in pre monsoon, one data monsoon, post monsoon kharif, and post monsoon rabi. So we kind of end up at the end of the year, we get only four values per year. So we can get only 4 months data. It's collected seasonally. So either the groundwater modelers are s- they end up with assuming that there is no change in the groundwater level apart from those 4 days, and they kind of try to use that kind of data, or they go for any other methods to see how the groundwater level can change. uh, it could be like an indirect method using ARC-SWAT or any other hydrological model which can give the groundwater level variation as a byproduct, and the groundwater modelers use it as an input for their groundwater modeling. So there is a lack of continuous spatial and temporal data that can make the groundwater modeling difficult. So the alternate methods could be like filling up the missing spatial and temporal values, and sometimes they go for base flow separation methods at both temporal and spatial scales, and sometimes they calculate groundwater from the water balance equation by using the ArcSWAT or HEC HMS or any other softwares. So these are kind of the indirect methods which people prefer in the absence of continuous groundwater data, both at spatial and temporal scales. But there is another way which we can go for, and that is we call data from sky. This is where the remote sensing of groundwater resource managers comes into play, and we try to use the gravimetry remote sensing data to remotely sense the subsurface water level. It's not possible with optical remote sensing since it's a hidden resource, nothing can be visible, but the gravimetric sensing can be done. So the gravimetry sensing, it senses the changes in the mass of terrestrial water balance components, like all the water that is included in our water cycle, starting from the atmospheric water to all the way to the groundwater. All the water is consisted in the terrestrial water, is called the terrestrial water balance components, and these changes kind of affect the gravimetry. balance of our Earth, and that's how the change in the gravimetric balance is sensed with the satellites. So the satellite mission, which is involved in this kind of measurements, is one of them is the GRACE satellite mission. It stands for Gravity Recovery and Climate Experiment, which is a joint mission by NASA, JAXA, and DFG. NASA is a US space agency, and JAXA is Japanese space agency, and DFG is the German space agency. And they combined, um, collaboratively, they work with the Jet Propulsion Laboratory in California to get the GRACE satellite mission running. Right now, the GRACE satellite mission is in its second version, so we call it as GRACE follow on or GRACE version 2. So, if you are interested in the GRACE satellite or GRACE satellite data, you can certainly go for it. It's freely available, and it gives data at the monthly scale, and it has a global spatial coverage. So the first problem which we encountered through our field data was that we were ending up with four data points or four values at the end of the year. But here we will get a monthly data set, and it has got a global spatial coverage, so there is no need to worry about that. If there is no well at certain point, then we won't be able to know how the groundwater level or the groundwater condition is at a certain place. The mass changes due to water movement or water loss can be detected at a very small scale, like at centimeter scales. The variation, if happens, then these satellites can sense it. So this has been used widely now, since they are free data sets, and they have got a global coverage. This is the map which shows the groundwater level variation using GRACE data in India, and how you can see that the centimeter per year, how these portions of northern India and around the Rajasthan and all the places, there is a lot of groundwater loss that is happening over the various months, or let's say if we are comparing it seasonally, how in different seasons they can be uh, sensed through the GRACE data. The GRACE data is available at 1 degree by 1 degree longitude and latitude approximately, which is like equivalent to 111 kilometer by 111 kilometer at equator. But since we are a little far from the equator, so we can get it at a even finer scale, but it still is like 100 kilometer by 100 kilometer scale. So it's 1 degree by 1 degree, which is still a very coarse spatial resolution, and this can be helpful in estimating groundwater variation for large catchments. But when we talk about smaller catchments, which are like less than 1 degree by 1 degree, the entire catchment, or maybe within 1 degree by 1 degree of grid, then this will not help. Like the GRACE data won't help us to use it for groundwater resource management. So when we say that the groundwater level variation can be sensed by ground GRACE data, and the spatial resolution is so coarse, a small catchment which lies within a 1 degree grid, there will be only one point data which we will get from GRACE. So that is kind of another downside of using the GRACE data directly. So my um, research was to use it at subcatchment scales. Since it has very limited application at subcatchment scale, I tried to use it and see if we can use it at subcatchment scale with four different case studies which I took. One with sparse network of wells. These are like 9 different grids I have taken in the state of Uttar Pradesh. And these 9 grids are GRACE grid, data grids, GRACE satellite grids, and the Ram Ganga, Ganga, Ghagra, Rapti, Jamuna. These rivers are flowing through those grids, and we have got around 400 plus well data, which gave us continuous well. And we tried to see if each of the four different cases which we have mentioned here can be used or can be implemented using the GRACE data. The first one was with sparse network of wells. This is the grid with sparse network of wells. Around 13 wells were there, and within that 1 degree by 1 degree grid, we got only 13 wells, and we tried to see if those 13 wells are showing a good correlation with the GRACE data. Then there are dense network of wells like this grid F, which has got like 72 or 78 wells, and dense network here in E and H. These are like the dense network of wells are present. When we say there is a dense network of wells, which means that we have got a lot of data sets, and each of the data set will be correlated with one single data value from the gray satellite. So there is a likely chance, statistically, if we are going for it, statistically there is a likely chance that we will get a good correlation with that. And then there is another case of wells near perennial streams, like the streams which are flowing here. We took the case of grid C, grid H, and grid I, and tried to see if there is a good correlation. And wells away from perennial stream, which is the case of grid B, there is no stream inside that entire 100-kilometer grid. So how these wells individually were able to uh, correlate with the GRACE data, if it is possible or not. And we use the machine learning technique. We have got a paper here. If you are interested, you can go through the paper. And we try to see if it is possible to use the GRACE data at such a small scale, like even it's not even a single big catchment, it's part of the catchment. It's like a very small place within 100. It's more like if we sum it up, it will be like 300 kilometer by 300 kilometer grid. So we try to see it, and there is this result with percentage of wells with good match with the GRACE data. So we find like where the 91.1% of data, like 91.1% of wells, they really match well with the GRACE data, and the GRACE data was able to capture very very small changes in the groundwater level. Now, when we say the groundwater level and GRACE data, there is a thing that the GRACE data gives gravimetric data, right? So the gravitational changes that is happening on the Earth's system, and that is being sensed by the GRACE data. But at this point, we should mention that they can't be used directly. They can't be used directly to uh, supplement for the groundwater level data which we get from the groundwater wells. So what we do, we try to correlate the GRACE data with all the different satellite precipitation, evapotranspiration, and all the data sets which I have mentioned before. We try to correlate and try to see how things are changing, how these parameters are changing in a water balance equation. How can we put these values, and can we see how they are changing, and is it giving a good value, it is a balance or an imbalance in the components. Uh, After that, we try to see the values which we get from the GRACE data if they can be used along with our groundwater or the ground data which we have for the groundwater from the groundwater wells. So this is a bit of an exercise, but still it's something. Oh, like we say, something is better than nothing. So in case of no data, this is some data which we can say. So, in conclusion, we can say the remote sensing and GIS methods can be used as an alternate approach for acquiring data for sparsely monitored catchments. Like there are many catchments you will come across in your life, which are not very regularly monitored or regulated, or there is hardly any data. In those cases, you can always rely on remote sensing and GIS methods for a like first step or a priori step before going into for the development of other monitoring or observation of things. You can do it. These are new and innovative method to fill in for missing data both spatially and temporally, because most people may be interested in research among you, so it's kind of quite new and innovative. So they can be used as a very what we say research topic, very interesting research topic, accepted ones, I will say. Even though it's not a direct source for groundwater label data, but the exercise, just as I mentioned, can give a very innovative start to your research if you're interested, and can fill in the gaps actually. And it's a better approach than using the indirect calculations for obtaining the groundwater level variations from than the surface water models, because the surface water models have kind of an unsaid inherent bias for surface water systems, so they may or may not be able to give you a very accurate groundwater level variation or groundwater storage component. So instead of going for a surface water model like SWAT or HMS or DHI models, it's better to go for some statistical models which can correlate and balance out the water balance components with the GRACE data. And this approach has been in use for groundwater resource management in the state of California. So it's kind of an acceptable method. And if you are interested, you can always go for that. And that's all. Thank you. If you are interested in contacting me, my contact ID is here. And thank you. Thank you for having me here. Thank you. Thank you for having me. Thank you. Hello, ma. Okay, okay, let me try. It has got a very low bandwidth today. Yeah, hi. Thank you, Didi. Thank you. If any questions, you can put in questions on the mail ID, or you can forward it through Dr. Komal. Okay, thank you. Okay, can I sign out now? Okay, thank you. Thank, thank you.